Hey guys, welcome to the continuation of our videos for the Putnam seminar. Well, I decided to go on with the videos since I've been teaching this course now at Tsinghua, the Fusion College in China. And I will continue where we were left last time when I taught this previously, starting the fall of 2020, with lecture 15.2, where we're going to discuss about more about integrals. And today I'm just going to show you an application of more of the techniques that we have you have seen so far, and I'm just going to dwell mostly on one Putnam problem. So let's get to it. So today we're going to talk about this Putnam B2 problem. So let me just go directly. So we'll study this problem, this Putnam problem. We'll dissect it in every possible way. So as you know already, I have told you there are 12 problems in total, each separated in two sessions. Each session has 6 problems. And this particular problem was a Putnam B2 in 2007. And well, it's considered to be not a super easy problem, but not a very hard problem either. I believe it's a little bit more than a B2 problem. So the problem has the following statements. So if I have a C1 function, right, on 0, 1, so basically a differentiable function with a continuous continuous first derivative, and its integral is 0 with no integral. So the integral from 0 to 1 is 0. So basically, we'll have to show that the integral from 0 to alpha for any alpha in 0, 1 is less than a constant times the maximum of the derivative in absolute value. And moreover, in fact, the tricky part is to show that this constant is actually 1/8. And moreover, this is sharp. And you will see that this problem is not trivial because, well, you can prove by some, more or less easy estimates that you can find 1/4, strictly less than 1/4. But 1/8, it's a little bit, so this is sharper. And moreover, 1/8 is the sharpest constant you can find. All right, so this is a statement. So basically what I'm going to do in this recitation is just to present to you this problem. In fact, I'm going to present to you more or less the 11 solutions. But also, since we're starting the anatomy of this problem, I would like to present to you some related problems, and basically solving those related problems, we'll go back and solve this problem eventually. All right, so before I dive into this, let me just a quick reminder of George Poya's advice on how to solve a problem. He wrote of this very nice book, How to Solve It. Well, his strategies was to first understand and where this problem is coming from. Well, and the thing is that if we understand all the words used in the problem, and if this will provide enough information for us to produce a solution, well, if not, then we need to devise a plan to attack the problem, and we can do that by using direct reasoning or look for a pattern, or maybe we can solve a simpler problem or a related problem, which basically we will do. What we will do also in this recitation, or maybe we have to be ingenious. Well, we will show that we have to do this as well. And now, after we have all this set up, we will carry out the plan, and we will go back and reflect on what on the solution we produced. So this is more or less the strategy of solving a problem. So Now, let me go and use some of Poya's strategies. And one of them was, as I mentioned previously, was to think of a simpler problem. And in fact, I will think of a simpler problem, and if I will, which is the problem that you see, but also I will think of a related problem, which will be a little bit more difficult. So this is a very standard problem in any analysis, real analysis textbook. And in fact, it appeared in this very famous Poya and Zegel textbook, Problems in Mathematical Analysis, has 3 volumes. So this problem appeared in volume 1. This is problem 121. You can find it at page 80. And I'm just going to give you a slightly modified statement. So basically, if I have a C1 function, and which is null on the boundary, so basically I have a differentiable function on AB, real valued, and f of a is equal to f of b equals 0, then I can estimate the integral of the absolute value of x. And as you can see, I have this 1/4 constant. So it's b minus a squared, everything squared over 4 times the supremum of f prime in absolute values. You see, so I have here the condition is a bit different. So basically the function is 0 on the boundary. Then I can prove that this is have a weaker estimate, but also on the left-hand side I have the integral of the absolute value of x, not the absolute value of the integral. And you know that the absolute value of the integral is less or equal than the integral of the absolute value of the function from the triangle inequality. All right, so let's look at this. This is not, I would not say it's a trivial problem. Well, it can get tricky at some point. So that's why you need to be careful once you do some estimates, and I'll show you where you can fall into a trap. I will present a solution and then a solution. Because you see, you have to prove that the integral of the absolute value of x, you have to estimate that quantity. So the main equation is the following. Do we know a solution? Maybe more, maybe for this simpler problem, like I said, simpler but not trivial. Well, let me give you the first solution. And the main idea is just to apply the mean value theorem. So the classical mean value theorem of Lagrange for differentiable functions on the intervals ax and xb, where x is arbitrary in the interval ab. So, and then the main strategy is to write the above integral as the sum of the 2 integrals on this on the intervals. So we're going to split the interval ab in a. We're going to take the midpoint of the interval. So if we have the interval ab, right? So AB, we're going to take exactly the midpoint, which is a plus b over 2. So basically, we will look at these 2 subintervals, a and a plus b over 2, so closed interval at both endpoints, and then we're going to look at the interval a plus b over 2b. All right, so let's do this. So let's apply the mean value theorem. So first, let's so basically, if we apply it on these intervals, ax and xb, we'll get this, that f of x is f of a plus f prime of c1 times x minus a for some c1 in ax. And then on xb, we'll get that f of x is f of b plus f prime of c2 times x minus b for some c2 in xb. So from these two, we can estimate simply. We don't, that's the thing, we don't need to integrate at this point. So basically, when we want to estimate. So once we do this, so if from the first one, so we'll get this estimate that the absolute value of f of x is less than m times x minus a, where m is actually the supremum of f prime, an absolute value. And then we'll get that f of x in absolute values m times b minus x for any x in AB. All right, great. And now at this point we can integrate, but pay attention. We have to integrate in a smart way. We're not going to integrate from A to B, so we're going to integrate from the first one from A to A plus B over 2, and then the second one we're going to integrate from A plus B over 2 to B. And in this way we will use the additivity of the integral. So let's get to the details. So once we do this, as you can see here, at this point, once we're going to use these two estimates. So we're going to integrate the first one. You're going to get here. So here we use in this first integral, we use the fact that f of x in absolute value is less or equal than m times x minus a. And here on the second integral, we use the fact that f of x is less or equal than m times b minus x. All right. Now, after you do some computation, and I'll leave this to you. So we just basic integration will give us that the sum is b minus a, everything squared over 4 times this times m. Okay, great. So this is the solution. So as you can see, we have to be extra careful with some stuff. And the main ingredient was just to the mean values theorem for differentiable functions of Lagrange. Okay, great. But you see, if we're not extra careful, let's see for another solution. And another solution, and you will see why. So basically, we will obtain a bit of a weaker estimate. And also, this would be a little bit fancy because we will use the Taylor series expansion. So let me just recall the Taylor series expansion. So if I have a function which is defined on some open interval I, and it's n times differentiable at some point a, and suppose that the n plus 1 derivative at x exists on that interval, then for each x different than a, there is a value c between x and a, such that we have this formula. So basically, I can write this as the sum of all derivatives all the way up to the nth derivative at point A. And here we'll have this remainder, which we call the Lagrange remainder. Which is f, the nth plus 1 derivative at this point c over n plus 1 factorial times x minus a to the power n plus 1. Well, this is, if you look at this, this is just a generalization of the mean value theorem. So for C1, you will obtain exactly the classical Lagrange mean value theorem for differentiable functions. But for example, for C2, so in the case of a function which is twice differentiable and the second derivative is continuous, so in this case of C2 functions, we will have this Taylor series approximation. As you can see, you have this extra term here, x minus a, everything squared over 2 factorial times f second prime of c for some c in a, b. So basically, we like to apply this in our case, but we will apply it for the antiderivative. So basically, we're going to do the same thing. So the idea is to do the same thing. So to apply Taylor's theorem for the antiderivative of f and I'm going to do the same trick. I'm going to split the interval into 2 subintervals. So the first one from a to a plus b over 2, and then the second one and I'm going to expand in Taylor series around the point x equals a. So that's the trick. And then when I look at the second subinterval, so a plus b over 2b, I'm going to expand it around x equals b. All right, let's do this. All right, so this is the first one. So I'm going to expand it, Taylor series around x equals a. Right, we're going to have this, so we'll have that capital F. So this is the antiderivative. So I want to apply for the antiderivative of my function f, right? So capital F, such that it has this property, right? As you know. And once I do this, for the first subinterval, I will obtain this relation. And then I'm going to do the same thing for the second one. And then I will have this. So if you look at the two formulas, we're more or less similar, right? You have the same quantity on the left-hand side, and it's a little bit different on the right-hand side, but no problem. We managed to do this. So basically, if we add these two quantities, so we will obtain that the integral from a to b of f of x dx, right? We're going to use the additivity of the integral, right? Here, the integral, basically this comes from the fact that the integral from a to a plus b over 2 of f is this plus the integral from a plus b over 2 to b of f of x dx is the same as the integral from a to b of f of x dx. And then we get this relation. So this relation here, and guess what? If we take the absolute value and we take into account that by the intermediate value property, then we will obtain this inequality. And then we take the soup. So we'll obtain this weaker inequality, unfortunately. As you see, we wanted the absolute value of, if you look on the left-hand side, we wanted the absolute value of the function inside the integral, not the absolute value of the integral. You see, we applied fancy stuff just to get some kind of weaker estimate, unfortunately. So we obtain a weaker inequality. All right, so this is a very similar problem. As you can see, that's it was an easier problem, a more standard problem. But now let's think of another problem, and which is, in fact, it's in the mirror of the Putnam problem, if you ask me. And this problem has the following statement. So this problem was given at the Romanian National Math Olympiad back in 1984. This is, well, long time ago. And if you see, it's very, very similar. Basically, it's the same thing after change of variable, more or less. So the problem has the following statement. If I have a function on 0, 1, which is differentiable, and such that there exists this constant a on 0, 1, but a is different than 0, such that the integral from 0 to a of f of x dx is 0. Then we can estimate the absolute value of the integral from 0 to 1, and we'll have this constant 1 minus a over 2 times the supremum of f prime in absolute value. So in what will follow, we will try to look at this problem a little bit, and I will show you a couple of solutions, maybe, I don't know, three solutions, and then after that, I think we were ready to look very closely at the original Putnam problem. All right, so let's see the first solution. As you can see, we would like to use we will use the mean value theorem. I think at this point it's a must. It's a standard ingredient. But first, let's do a change of variables. If I take x to be at, then I'll have this condition here. So basically, I will just apply the mean value theorem, right, for this function. G of t is f of tx. I'll consider this on the interval a1. So basically, if you look at this, and if you apply the mean value theorem, then f of x minus f of ax in absolute values less or equal than the supremum times the x minus ax in absolute value, which is m times 1 minus a times x. So this is the main relation that we have here. And then at this point, since we know that the integral from 0 to 1 of f of ax is 0, we can put that inside. And in fact, here, in fact, this is a bit of a mistake here. This should be equal here. And this is less or equal than the integral from 0 to 1 of f of x, of the absolute value of f of x times f of ax, just to be precise, the x. And now you can use this estimate here of f of x, the star estimate, and then by using star, you will get this one here. All right, and then at this point, it's just an integral. So this is a standard solution. Right? All right, but maybe we have some other tools in our hand, and we can use some other ideas. We can approach this problem in a different way. And you've seen that I gave you that solution, which unfortunately provided me a weaker estimate, but we use some fancy Taylor expansion. All right, let's do it. Maybe we're more lucky in this case. And yes, we can do it. And let me just first, let me observe one thing. So I know that the integral from 0 to a is 0, so no problem. I will just split this integral from 0 to 1 into the integral from 0 to a of f plus the integral from a to 1 of f. Since this is 0, then we know from the hypothesis that this is 0. So this implies that the integral from 0 to 1 is the integral from negative the integral from a to 1. All right, so basically I will have to estimate that once I change. This is nothing else than the integral from 1 to a of f. All right. Let me consider the antiderivative of this, right? Big F prime of x, and I'm going to apply the Taylor's expansion theorem for the antiderivative around the point x equals a. So once we do this, we have that that f of x is f of a plus x minus a over 1 factorial times f prime of a. And now the second order will be x minus a, everything squared over 2 factorial is f second prime of c, for some c in 0, 1. And now I'm just going to take x to be 1. And then this relation here will be just this. So as you can see here, this guy, f of 1 minus f of a, it's exactly the quantity we need so that we can deal with this integral, so that we can estimate. And now at this point, we have this. And for x equals 0, if we look at x, we have this here integral, but now for x equals 0, if we plug in x equals 0 and this formula, let me call this double star. So for x equals 0, we'll have f of 0 minus f of a is negative a times little f of a plus a squared over 2 times f prime of c for some c in 0, 1. And of course, I will have this other relation. So basically, which will be equivalent with this relation here, regarding this integral. All right, and then clearly it follows that we will have this estimate. So f of a, since the integral is 0, then I'll have that f of a is less or equal than this. So f of a in absolute value is less or equal than a over 2 times the sup norm of f prime of x in absolute value, and this is 0 to 1. All right, great. Let's put everything together. So we put everything together, and at this point we can estimate here, right? Because look, I get this integral here. So the integral from 0 to 1 is less than 1 minus a times a over 2 times the sup of f prime, absolute value, plus 1 minus a everything squared over 2 times the supremum. And then after just doing basic algebra, we'll get the conclusion. Exactly this. All right, so this was a fancy, let's say, proof. All right. But maybe there is something more. And so this is the second proof. Maybe what about convexity? Maybe I told you at the beginning, maybe we can come up with the ingenious idea, just coming from something out of nowhere. If you look at this problem, you will say like, well, mean value theorem makes sense. Taylor theorem makes sense, but convexity, that doesn't quite make any sense here. I mean, there is nothing about convex functions. Well, there's an estimate about the derivative, but still, I mean, convexity it's not obvious how you can come up with convexity in these kind of problems. All right. But first, before we go into that, let me just remind you the definition. So it's surprising that this notion was invented. I'm still astonished, even to these days, that this notion, which basically now it's in Calculus 1 textbooks, in many introduction to analysis textbook, was surprising to me that it was first invented in 1906. So a little bit more than 100 years ago. There's this very famous paper of Jensen, Acta Mathematica. Yeah, it was very shocking to me to find out this. So basically, it's such a natural notion. For A and B, with A less than B, we say that we consider this phi from on the interval A, B, real value function. We say that phi is convex if phi of 1 minus lambda times x plus lambda y is less or equal than 1 minus lambda phi of x plus lambda phi of y. This happens for any x, y, and AB, and for any lambda and 0, 1. So basically, geometrically, if you look at this function that takes lambda all the way to this line segment, this parametrization of the line segment, which is given by 1 minus lambda x plus lambda y and 1 minus lambda phi of x plus lambda phi of y. So this is just a parameterization of the line segment in R2. And of course, the inequality is reversed if phi is said to be concave. So basically, if you look geometrically, convex holds the water, concave does not hold the water. But let me just go a little bit, dive in something that you know. But let me just give you a quick reminder. Well, if you look at the line segment, right, if you take x phi of x and y phi of y, if you take these 2 points, these 2 endpoints. So there is a chord of the graph of these 2 points, right? You have so basically you can interpret the definitions of concavity and convexity as follows. So we say that the function phi is convex if every chord lies above the graph of f, right? Basically, you have something like this. This is the graph. So every chord lies above the graph, right? Something like that. And concavity is the other way around. So every chord lies below the graph, right? So something like this. Anyway. And there is this characterization. There is a relationship between the differentiability and convexity. And this is just the derivative test, the second derivative test, more or less, which is standard in any basic calculus textbook. The theorem says the following. Basically, given a twice differentiable function phi from R to R, we say that phi is convex if the second derivative is non-negative for all x in R, and if this implies convexity, but if the second derivative is negative for all x, then phi is concave. You can see this is a great way to characterize functions Well, for example, I don't know, you have plenty of examples of convex functions. You can take, I don't know, x squared or e to the x. And concave, you can take the natural log of x and so on. Plenty of functions. All right, now let's use this notion of convexity to give a third proof for the problem given at the Romanian National Math Olympiad back in '84. So we're not solving the Putnam problem yet, but this is so similar that at this point we have all the techniques, all the ingredients to give plenty of solutions for the Putnam problem. But we'll go over that in a moment. All right. So again, let me consider m to be the maximum of the absolute value of f prime of x on 0, 1. And we're going to define this very this auxiliary function. So g of x is negative the integral from 0 to x of f of t dt plus m over 2 times x squared. What I'm going to do is, if you look at it, the derivative, you take the second derivative of this, it will show you, right, that the function is convex, all right? G prime, so I'm just going to leave this to you as a computation. G second prime of x is now negative for all x. Great. No problem. Then I'll do this trick. So I'm just going to write, so this implies the convexity of G. So I'm going to write G of A as G. I'm going to parameterize this I will use convex parameterization. There's very tricky convex parameterization. So basically it's G of 1 minus A times 0 plus A times 1. So since G is convexity, so here I use the convexity, the definition. So once I do this, then this will be less or equal than 1 minus A times G of 0 plus A times G of 1. But since G of 0, if you look at G of 0 is 0, keep that in mind. If this guy is 0, like just replace x equals 0. So, and this will be A times G of 1. All right. So basically, if we'll just rewrite this inequality, so don't forget who G of A is. So I'm just going to replace it here. So I'm just going to rewrite this inequality, and this will be equivalent with this. So negative the integral from 0 to A of f plus m over 2 times A squared is less or equal than A times, so that G of 1 is negative. So this guy is G of 1 here. Right, and this is G of A. That's exactly what we want to write this. We write this inequality. And of course, we're going to do computations at this point. This implies that since we know that the integral from 0 to A is 0, then this will imply this estimate, which basically solves our problem. As you can see, if we just construct a surprising function, which happens to be convex, then we can actually provide a very surprising solution, unexpected, I would say, to this the Romanian National Math Olympiad solution in 1984. So let me just go back and so basically I was talking about this problem, right? So this is the problem here. But this is very similar to the Putnam problem. Now we can dive in and solve the Putnam problem. So let me just go quickly and the statement. So keep in mind that the statement was this one here. So we have a function which is C1 function with null interval. So we have to estimate the integral from 0 to alpha for every alpha in 0, 1. And it's given by, this estimate is given by this constant, which is 1 over A times f prime of x in absolute value. Okay, let's dive in directly. So So maybe before I go into that, let me just briefly present. So I'm going to give you 11 solutions for this one. I'll present 11 solutions. You'll see all sorts of techniques. And in fact, we will use convexity in many ways. All right. So the official solution that you can see on the Putnam webpage, you can look at Kedlaya's webpage. Is a webpage maintained by Kiran Kedlaya, where you can see all the Putnam problems and their solutions as well. So this is the official solution that is presented there. So if we take the B to be the maximum of f prime of x, the absolute value of f prime of x, and g of x to be the integral of f, then clearly g, the thing is that since g of 0 is g of 1 is 0, then the maximum value of g prime of g of x in absolute value must occur at the critical point y, which of course, since it's a critical point, will satisfy that g prime of y is 0. So since g prime of y is f of y, then we'll have that f of y is 0. And then we can take alpha to be y hereafter. All right, great. So basically, since now the function is symmetric, as we look around 1/2, then I can assume that alpha is less than 1/2 because I have this symmetry condition here. So I can assume this. And from this, I think it's pretty clear. So since the integral, without loss of generality, I can assume that the integral is non-negative. And then since the f prime, the derivative is greater than negative b, then I will just have that the integral, that the f of x is less or equal than b times alpha minus x for any x in greater than 0 and less than alpha. And then I will just integrate. So basically, you just integrate this and you'll get this here. And then there you go. You get this estimate. All right, so that's the official solution. It's not hard, but I must confess, I was talking to some people about this problem. Some of them came up with this solution. I must confess I did not come up with this solution, but I'll present some other solutions. So this is the official solution that you will find also in their on Kedlaya's web page. All right, so now let me present you another second solution. Like I said, we're going to have 11. Oh my. All right. So the second solution is basically it's very similar to the first solution for that Romanian Math Olympiad problem. This time, I think those problems were in mirror, basically. So this time, since I have this integral, I want to evaluate, to estimate this integral from 0 to alpha. Then maybe I'll do a change of variables, x to be alpha t, and then the integral from 0 to alpha of f, it becomes the alpha times the integral from 0 to 1 of f of alpha t. And then I will just, since I know the fact that the integral from 0 to 1 of f of t dt is 0, I'll insert it here, and then I'll apply the triangle inequality. So here is just the triangle inequality. And now by using the mean value theorem, we're gonna, once we apply the triangle inequality, and I'm looking at this quantity here, I have the integral of this quantity, and then this I will estimate it by the classical mean value theorem for differentiable functions. Okay, great. So this means that I can write that f of t minus f of alpha t is f prime of c for some c in alpha t, this integral alpha t times t minus alpha t, all right? And now, great. Once I can estimate this by the supremum, and then I'll have this inequality right here. So f of t minus f of alpha t in absolute value is less than m times t times 1 minus alpha. Great. Now I can integrate, and once I integrate, basically I'll get that the integral from and do the change of variables. I'll get that the integral from 0 to alpha of f of x dx is less or equal than alpha times 1 minus alpha times m, which basically is less or equal than 1 times 1 over 8 times m. Well, throughout let me mention one thing. Throughout all solutions, we're going to use this estimate here, and in fact, this can be proven in many ways. For example, you can use the first derivative test, or you can use the AMGM like this. This is the AMGM. This guy would give us 1 over 4. I'm going to use this over and over again, so I'm just going to explain it now. So as you can see, let me point out this remark. This solution is very similar to the first solution that we gave for problem 2, right? That problem from the Romanian National Math Olympiad that we just discussed previously. All right, great. But remember, in that Romanian National Math Olympiad, we also gave a Taylor using a solution using Taylor series, right? And we also attempted to prove the Poyas problem from his textbook using the same approach of with Taylor series. So let's try to do the same thing here. And so this is the closest to the solution that I initially gave when I first saw the problem. So let me just consider the antiderivative. So f of x is the integral from 0 to x of f of t dt. So now what I'm going to do is the following. So I'm going to look at the square of the antiderivative, and I'm going to take a value. I'm going to consider a value a, 0, 1, at which f squared is maximized. All right, first, let me, if we, by the fundamental theorem of calculus, clearly f squared, is differentiable, and its derivative is 2 times f times f, right? Now, if the big F at a is 0, then there is nothing to prove. Well, this means if not, then this means that f of a is 0. And now what we're going to do is just I'm going to expand the antiderivative in Taylor series around that point where f of a is 0. So basically, I'm going to take this into account. So that's the trick. Right? I write the Taylor series expansion for the antiderivative. And once I do that, so I can write f of x equals f of a plus x minus a times f prime of a plus x minus a squared over 2 times f second prime of c for some c between a and x. So I'm saying between because I don't know which one is bigger, a or x. Great. I'm going to do what I'm going to do right now. So I'm going to take this. I'm going to see what happens at 0, what happens at 1. Great. At 0, we have this relation here. For x equals 0. So f of 0 is f of a plus a times f of a plus a squared over 2 times f prime of c1 for some c1 between 0 and x. Now at x equals 1, I'm going to do the same thing. So I'm just going to look at this relation here at x, 0, and 1. So we're going to have this. F of 1 is f of a plus 1 minus a f of a plus 1 minus a squared over 2 times f prime of c2, of course, from some c2 between a and 1. Great. Now, basically, this will imply the following two estimates. So f of a, an absolute value, so the antiderivative at a is less than, we have this estimate. But also from the second one, we have that f of a is less or equal than 1/2 1 minus a squared f prime of c2. All right, great. Now, once I have these two in hand, I think I know how to estimate here. Basically, I'm just going to consider the this f of x. I'm going to write it as the square root of f squared of x, which is less or equal than the square root of f squared of a. But this is the square root of f of a times f of a. But for one f of a, I'm going to use the first estimate here. And for the second one, so here I'm going to use this by 1. Here I'm going to use this by 2. Great. So once I do this, and putting everything together, I will end up with this, which is less. And once I take the soup for each one of these, then I'll have this estimate. And finally have my conclusion. And of course, where we have used the fact that this is less than 1/4. So as you can see, very tricky solution using Taylor series. This time we have to specify. So we use the Taylor series exactly at that point. You see, because you can see where exactly at that point at which f squared is maximized. Okay. Now, okay, we said something about convexity. Maybe it works here as well. Of course it does. But here is actually even more direct. It's pretty simple. See, in the previous problem, it's just a slight modification of the idea from that problem. So basically, instead of a negative sign in front of the integral, we're going to take a positive sign. But you see, the thing is that this function is a convex function. Again, if you look at the derivative, is now negative for all x in 0, 1. So this guy is not negative. So again, I'm going to write it this way. I'm going to parameterize this convex parameterization. G of alpha is g of 1 minus alpha times 0 plus alpha times 1. And by the convexity, so by the definition, this is the G convex. So we're going to use it here. This is less or equal than 1 minus alpha g of 0 plus alpha times g of 1. And of course, we're going to write this. So now we're going to write this because we know who g of x is that in this expression here in the blue. All right, and now we're going to do computations, and basically it's the same thing. So we're going to end up at this point after we just rewrite this expression. We're going to end up with this inequality here. And of course, we're going to use that this guy is less than 1/4. And there you go. We're going to obtain exactly our estimate for any here alpha in 0, 1. All right, great. Fourth solution. Oh my. The fifth solution, in fact, we can use convexity again, but I'm going to tweak it a bit. This time, I'm just going to consider this function, g of x, and you see, I'm going to take this x squared minus x. G is convex, again. The second derivative is not negative. But moreover, if g of 0 is the same as g of 1 is 0, so therefore this means that the function is negative. So there you go. So this means that this guy is negative, and if you write this, you'll get exactly this estimate. So this is even a more direct function if we tweak it a little bit. All right, had enough of convexity? Maybe I'll get back to it. But so far, two solutions using convexity. All right, let's leave convexity for a bit. I didn't want to give it too much convexity. Maybe I'll go back to Taylor series again. Okay. You see, Taylor series, maybe I'll have a more of a direct Taylor series approach to this. So if I consider f of alpha, so this is the antiderivative, and I'm just gonna do a Taylor series expansion for alpha evaluated at 1, right? So basically, we're gonna expand the function at alpha, around alpha, but then I'm gonna evaluate this at 1. So basically, if once I do this, then I can write it in this way. You can see here, so this is the Taylor series expansion. And then for some from some beta in this interval alpha 1. But we also know from the hypothesis that f of 1 is 0. So basically, the maximum values of the absolute value of f of alpha, we will have that f prime of alpha is 0. So therefore, we can obtain that this happens. And then at this point, this is pretty clear because we know that we can assume the maximum occurs since by symmetry occurs at when alpha is greater than 1/2. So basically, we can estimate f of alpha in absolute value, and this will give us exactly the precise constant, which is 1/8 times the maximum of f prime, little f prime of f. So basically, this is what we want. So you see that the Taylor series approach is more direct than the previous one. All right. All right, but we see I showed you a bunch of more or less of tricky techniques, more advanced. But why we should go back to the basics? What if we can do some integration by parts, for example? And sure, we can do it. So basically, I'm just going to look at these two integrals from 0 to alpha of f, and I'm going to integrate it by parts. And you can see the function inside that I'm integrating xx minus alpha prime here, which is 1. Once I integrate by parts, I'll get this formula here. And now what I'm going to do is to see what happens when alpha equals 1. Well, when alpha equals 1, I can write it in this way, which is very nice. And now what I'm going to do, I'm going to combine these two. So combining these two and basically writing, knowing the fact that this integral is 0, let's take this into account. So I can write that the negative integral from 0 to alpha of f is alpha times the integral from 0 to 1 of f minus the integral from 0 to alpha of f of x dx. And now, basically, I'm just going to use the two identities here, right? And once I do this, I'll get that I'll get this difference of integrals. And at this point, basically, which will give us this. So this integral here is nothing else than just this sum of these two integrals. All right, great. So now I can take the absolute value on both sides. So once I do this, and I'm just going to take the soup, then the problem just goes. It's pretty straightforward. Again, we just use the same estimates. Alpha times 1 minus alpha is less or equal than 1/4. So basically, it goes pretty straightforward, just like I said. So you see, this is the 7th solution, which used more or less basic stuff like integration by parts. Let's do integration by parts again. So the 8th solution. Well, again, I need to show, if I consider f of I to be the integral from 0 to a of f, I need to show that f of a is between m/8 and negative m/8 and m/8 for a in 0, 1, where m is the max of absolute value of f prime of f. prime of x, right? Okay. Great. So the main idea, so it's enough for us to see that we need to check the above inequality. So this one here, we need to check it only at the point where f of a is 0. A is between 0 and 1. All right. So the main idea is to express f of a in two ways using integration by parts. All right. So once we do this, so if I write f of a, I can write it in this way. The integral is basically its formula. So once I do integration by parts, I will get this, right? But also, on the other hand, let's take into account that this is also the integral from 0 to a is the integral from 0 to, using the additivity of the integral. Then this is this as well. But we know that this integral is 0. So this is nothing else than just this. Again, using integration by parts, we'll get that f of a is this integral here. Standard integration by parts. So on one hand, we have this, but on the other hand, we also have this. Okay, great. Now we combine these two. So basically, if we take the absolute value and we're going to take the soup, then from the first integral, we'll get that f of a is less or equal than a squared over 2 times m. And then from the second one, we'll get that f of a in absolute value is less or equal than 1 minus a squared over 2 times m. Now, we use the fact that we're going to multiply them. We're going to use the fact that the same inequality as we have been keep saying, and then we're going to get exactly the estimate that we want. All right. See, integration by parts again. Okay, but now let's see with the ninth solution. Let's see convexity again. I'll be even more precise now. What if we consider this function? So one final convexity tweak. So what if we consider this function here? Again, if we consider this function, this so g second prime of x, again, no negative. So basically, it's a convex function. And of course, g of 0 is g of 1, which is m over a. So since this is convex, then this means that it's greater or lesser, g is less or equal than the value, on the boundary of g, so basically which is m over 8. So g of x is less or equal than m over 8. So you do the computations and everything, you will get exactly the conclusion of the problem. All right. Now, well, we have something that we haven't used, which is Rolle's theorem. You can do it even using Rolle's theorem. And this is again another very nice solution. So for each fixed x in 0, 1, we're going to define this function, a capital A of x, such that the integral from 0 to x of f of t dt is the same is a of x over 2 times x minus x squared. As if you look at it, this is just a linear equation, so you can solve it for a of x, and then we can write a of x like this. All right, great. But now what we're going to do is I'm gonna define this function here, g of y, to be, and I'm gonna want to use Rolle's theorem to this function, g of y, or to its derivatives, is the integral from 0 to y of f, basically this function here. This is my surprise function. This is my function g of y. So I'm going to define this function, and I'm going to play a bit with it. So, okay, clearly it's a differentiable function. So let's do, by computing the first and the second derivative, we'll get that the first derivative of g is f of y. So again, this is a function in y, pay attention. The first derivative in variable y is f of y minus a of x over 2 plus a of x times y. And the second derivative is f prime of y plus a of x. Great. So what I'm going to do right now, clearly g of y is 0. If you look at it, look at this, g of y is 0. When is this 0? When y is 0, y is x, and 1. So these two go very great. So what I'm going to do, I'm going to apply Rolle's theorem on. So I have 3 points. That's perfect. I'm going to apply Rolle's theorem on each on these. So these 3 points will determine 2 subintervals. So I'm going to apply Rolle's theorem on each subinterval. Okay, let's do it. I'm going to apply from 0 to x, and then to x on the interval 0x, and then x1. So on 0x, I'll have these number a. So basically, there exist numbers a and b, a in 0x and b in x1, such that g prime of a is the same as g prime of b and is 0. Great. So now I have that the derivative at these 2 points is 0, no problem. I'll apply a Rolle again. So there exists this means that I can g second prime of psi is 0 for some psi in this subinterval ab. This AB is subinterval of A. So this implies that f prime of psi is negative a of x, right? Because we have this relation here, you can see. All right, so I'm basically now I'm going back to the initial, and I'm just going to write it. So basically, we're going to conclude that there exists a psi in 0, 1, such that the integral from 0 to x of f of t dt is negative f prime of psi over 2 times x minus x squared. And of course, from here, I just take the absolute value. I'm going to do the estimate here that I keep mentioned, and that's it. That's the problem. So again, we can even use Rolle's theorem. It was a little bit complicated and very, I would say, artificial, but it's a very beautiful solution as well. Well, hold your breath. We're not done. We can give another solution. And there is this notion, well, I'm going to define it, and I'm going to, of what we call Lagrange interpolation of of C1, C2, and so on functions. Well, usually, and of course, this Lagrange interpolation, we were going to use this interpolation polynomial due to Lagrange. It's not usually done in, although it's something basic, I consider something basic, but it's not usually done in basic real analysis textbooks for some reason. I don't know why. I haven't seen it in many, but it is done in any introductory course in numerical analysis. It's like a must for proving this quadrature formulas. So basically, you can estimate integrals in terms of their derivatives and so on. All right. So first, what is a Lagrange interpolation polynomial? So let me just go give you a little bit of a context before I just tell you the main theorem. So the main problem, this stems from the following problem. So given the values of a function, let's say we have a function f of x, And given the values at n plus 1 distinct points, let's say x1, x0, x1, xn, and f0, f1, fn, where these fi's are f of x I, so these fi's are the values of f of x, these xi's, from I from 0 all the way up to n. And what we're asked is to find a polynomial of degree n, p of x, such that p of xi is fi. All right? Let's look at the simplest case, n equals 2. And you will see where the idea comes from. So basically in the case n equals 2, so I have these points x0, x1, and f0, f1, right? These are the values of f at the points x1, x0, and x1. So we want to find, in this case, a polynomial of degree 1 such that p of x0 is f0 and p of x1 is f1. So how are we going to do? So the main idea comes from the equation of a line as follows. So you can write y is f of 0 plus, so here we have the slope f of 1 minus f of 0 over x1 minus x0 times x minus x0. And we've rearranged this, and we can write it in this way. Wow, this looks very nice. So basically, if we denote these two polynomials here, this first degree polynomials, let's say L0 of x, this guy here is L0 of x. This guy here is L1 of x. This is x minus. So these polynomials, if you evaluate at x0 and x1, they satisfy these relations, right? So L0 at x0 is 1, L0 at x1 is 0, and L1 at x0 is 0, and L1 at x1 is 1. So basically, I can write my polynomial p of x as this combination f0 L0 of x plus f1 times L1 of x. So basically, this is nothing else than just the unique linear polynomial passing through the points of coordinates x0, f0, and x1, f1. So in other words, we have that if we evaluate this polynomial of x equals x0 and at x equals x1, therefore, then we will have that p of x0 is f0 and p of x1 is f1. Okay, that's great. So basically, let's look at the general case. So in the general case, so the general case is for n plus 1 points. So we were given this x1, x0, x1, xn, and f0, f1, fn, which are the values of f at the xi's. And we're going to consider these special polynomials, Lk of x, such that Lk of xi is 0 for all i's except k. And at this particular point, xk is 1. So basically, these polynomials are 0 at all points except for 1. Well, a polynomial of degree n, which is 0 at all points except xk, is given by this guy here. So I'm just going to take all the products. And as you can see, what is missing here is exactly this x minus xk is missing. So this guy is missing. So if we want that polynomial to have value 1 at xk, then we must divide by its values at xk. In other words, we need to define the basic Lagrange polynomial of degree n, which is given by this fraction here. We have the product of this. So basically, it's the same thing. The only difference is that I put here x on the top is x minus x0 times x minus. So it's exactly what we have here. But on the bottom is the same thing, but instead of x, I evaluated at xk. Okay. So basically I have that this polynomial. So once we will interpolate this, then I can write, just like in the case when n equals 2, I can write p of x as f0 times L0 of x plus f1 times L1 of x plus so on, fn times Ln of x. This guy here, this p of x, is called the n Lagrange interpolating polynomial. And of course, when we evaluate at xk, we'll get exactly those values fk. And now we can state actually the theorem. And it's a very nice theorem, which you will see that it will come to our rescue when we'll go back to the Putnam problem. So basically, the theorem states the following. Suppose that I have that these points, these n+1 distinct points in the interval a, b, so x0 all the way up to xn. And f of x has n+1 continuous derivatives. Then for each x in a, b, then there exists some c which depends on x in the interval a, b, such that f of x is the Lagrange polynomial, which is p of x, that the nth Lagrange interpolating polynomial, plus this error term. And this error term, well, it kind of looks like it resembles a bit the Lagrange remainder, but it's not quite the same thing. So it's the n+1 derivative at that point, c of x, over n+1 factorial times x minus x0 times x minus xn. So I can write this, which is great. So this is the main theorem, which we will apply in our case. And in our case, we'll apply this theorem for the antiderivative. So the antiderivative will be C2. All right. So let's give another and final solution, 11th solution. So basically, this I will do it in a more general fashion. So instead of 0, 1, I'm just going to take a, b. So if I consider the antiderivative, so f of t is the integral from a to t of f of x dx, and I'm considering p to be the Lagrange interpolation polynomial of f at the endpoints, x equals a and x equals b. By the approximation theorem, or by Lagrange interpolation, then I can write it in this way. So f of t is p of t plus this, or I'm going to rewrite it in this way, I have this. And I think from here, the problem follows pretty immediately. So as you can see, it's exactly the same thing, right? So f of x minus p of x. In our case, f of x is this guy here. So we're going to apply the Lagrange interpolation theorem over this. And then I will go for the second derivative of f, big F. I'm going to write it. So this is translated into this. But we know that P is the zero polynomial, since P of A is f of A and P of B is f of B. But this is nothing else than just the integral from A to B, which is 0. Wow, this is great. So this means that I can just estimate this guy here. The only thing I need to take care of is this guy here. All right, great. This is nothing else than this is f prime of ct. So once I take the absolute value and I estimate that this guy will be, this is will be equal to this. And now this guy by the AMGM, right? So by the AMGM, so once we do all this algebra, by the AMGM, we'll have this inequality. So this guy will be estimated by this. So it's pretty much the same thing. And now, which gives us this inequality. And now we just, in the particular case, when a equals 1 and b equals 1, a equals 0, sorry, and b equals 1, we'll get our problem immediately. So yeah, there you go. See, it is pretty, once you use Lagrange interpolation theorem, the solution is pretty direct and straightforward, but modulo this notion, which is, like I said, not learned in it's not super standard in any classical analysis textbooks. Anyway, so, well, over the course of more than an hour, you have seen a bunch of techniques, 11 solutions for the Putnam problem. But now I'll present to you, well, I'm not gonna go into not gonna spend more than another hour for this, but I'm gonna leave it to you as an exercise, which is very similar. So basically, if I'm going now a little bit up to C2. So if I have a C2 function, and then I impose an extra condition, f of 0 equals 1, then I can estimate here all the way up to the absolute value of the second derivative. And the constant was very sharp, is 2 over 81. So I'll leave this to you as a, so this is just a small variation of the Putnam B2 from 2007. And I think I'm gonna stop here. Thank you.